Hello, this video is confidence intervals for the mean, population standard deviation unknown. So we've had a previous confidence interval section to where this population standard deviation was known. Now we're just going to have the sample standard deviation, which is probably what you would have in most cases anyway. Now we have a new type of distribution called the t-distribution, also known as the student's t-distribution. Student just happened to be the name that the guy that created this, Gossett, that was his name he published under. Arises from the problem of estimating the mean of a normally distributed population. When the population standard deviation is unknown, has to be estimated from the data. Okay. Let's look at some of the characteristics. The t-distribution is a continuous bell-shaped distribution, symmetrical. But the key here is there's not one t-distribution, but a family of t-distributions. And the actual shape of the graph is going to depend on what the sample size is. And they mention here that the graph's a little bit flatter than the normal distribution. So what's going to happen here is these are based on, I'll talk about what that DF means there in just a minute, but it's different shapes graphs based on size n. So therefore your critical values are going to occur at different locations based on the graph based on what n is. So for example, when we're doing the z distribution for 95%, and this one's 95% right here, and they're showing the infinity, that it's 1.96, always if it's a z distribution. Otherwise, it's going to be a t-distribution, and it's going to have different values. You don't have to worry about this calculator business over here. I wouldn't worry about this because it's not really that helpful. It's probably easy just to use the chart anyway. Now the conditions, the t-distribution, the original data still has to be normally distributed. It's still, you're coming from a normal population, but you don't have the population standard deviation. We have the sample standard deviation. Now there's something very important here called the degrees of freedom, short for DF, and that's if you've watched the video or looked at the notes for I didn't use this term at the time, but because we didn't need it. But there's that DF right there is degrees of freedom. And it's always calculated as n minus 1. Very important that we remember that. So like I mentioned here, if they tell you in a problem the sample size is 20, the degrees of freedom will be 19, because that's very important on getting our critical value from our chart. So let's see what we have here. So there's the t-distribution chart. And we're still going to use the same confidence levels that we used before up here across the top. One thing we're not going to do with the t-distribution like I did with the z was coming up with critical values at just random percentages. I had an example where we did one, it was like 82% or something like that. It's too complicated to do that here. So we're only going to use the ones that are in this top row. So but then you go down now though, instead of just using the top row, we have to pick the correct row for the degrees of freedom. Now the degrees of freedom, if you really wanted to investigate this, you could. It's kind of actually complicated on the reasoning behind it. I put a little blurb here at the end of the notes. You don't have to look, I said, just informational purposes only. Like this real quick, I'll mention this example. Like you have x plus y plus z equals 15. That 2 is just, I don't like the way they did put that 2. They should have put it in front because it looks like it's 15 times 2. But if you have x plus y plus z, 3 variables, and you know 2 of them, that means you have 2 degrees of freedom of choice, because if you pick a value, you choose a value for X and Y, that's what I meant to say. You choose a value for X and Y, you can't choose Z. Z has to be whatever it is. So like, for example, if X was 3 and Y was 7, and I just made those up, I can't choose Z. Z would have to be 5 to make it equal 15. So you essentially had 2 degrees of freedom. But more in our use, it has to do like over here where it talks about this involving the sample mean. If you knew the sample mean, you could know you could have all the values, but one of them, then you'd have to calculate what that one missing value would be. But that's all right. You don't have to worry too much about it, and it gets even more complex than this. All you have to remember is n minus 1, and you're good. Okay. Now I want to mention this a little bit here, sort of the differentiation between Z and T. Now, it's really based on the standard deviations, the ultimate. If you have the population standard deviation, you use the Z. If you have the sample standard deviation, you use T. Some authors, though, kind of use that 30 rule like we have for the central limit theorem. They'll say if n is 30 or more, you can go ahead and use the Z. But because what happens is, if you look at these, this is only up to 29, obviously, but let's just pick this 95% column. You start going down this column, eventually as the degrees of freedom, which is just one number less than n, so when I'm at 29, that means n is 30, it's decreasing to where eventually T becomes Z. So for example, it really wouldn't matter if your sample size was 200, whether you use the T or Z, because T becomes Z over time. In fact, that's the whole idea of the infinity degrees of freedom right here in the top row, is the increasing of the sample size. It just morphs into one thing there. But 30, maybe is a little bit too small to sort of justify that. So what I like to do, so in addition to, using the precise definition of the population standard deviation versus the sample, I also take it one step further, and the problems that I would ask on an exam, now my math lab homework might be a little bit different, but what I would ask on the exam is, if it's going to be a Z distribution, not only will we have the population standard deviation, I'm going to make sure that the sample size is more than 30. And then the T distribution will be sample sizes. I'll just strictly stay less than 30 for the T, and that way there's really no confusion. You can kind of use the 30 rule if you want to, in addition to the standard deviation. But just to kind of give you an idea, technically, if n was 15 and you had the population standard deviation, you could then use Z. But I'm going to make sure that doesn't happen. All right, so in fact, when I give this exam in class, I just give that one page of that. There's in my notes in our Blackboard, I have, I think, a few pages of this, and you might need higher degrees of freedom to do a homework problem, possibly, my math lab homework. But on an exam, I just always give this one page, because I know that my sample sizes are less than 30, so you would never need more than that one page. So if you want to read that a little bit, you can. So let's practice finding values off that chart. So let's see if we can find the critical value. And once again, you can completely ignore this calculator business here. I wouldn't even worry about it. I just did it. Actually, the calculator's only has this function for the 84 or higher. The 83, TI 83 doesn't even have this. But we don't need it. So suppose we're going to find a critical value for the T distribution. Now I'm just using T alpha over 2 instead of Z alpha over 2. So let's say it's 98% and n is 13. So if n is 13, we have 12 degrees of freedom. Let's come back up here. And I think I'll just kind of put a mark around this. 98%, 12 degrees of freedom. Sort of doing this with a mouse pad, not with a pen. There we go. it would be 2.6810. And it's almost a guarantee, I say almost, that on an exam, I always ask a question like where you have to find the critical value. There's almost no doubt that the answer below it is going to be there, because the skill of this is knowing that you have to subtract 1. So I would probably have 13 as an answer choice and then 12. But 12 is correct because it's 13 minus 1, 12 degrees of freedom. So just be real careful when you're reading that chart. And there it is, 26810. If n is confidence level is 80% and n equals 24, we subtract 1, we get 23. So 80% and 23 be right down there at the bottom. $1.3195. Okay. And there it is. Oh, I just happen to have the old Z formula there, and I probably wrote that down there and just forgot to save it without it being there. But I'll leave it there just for a second, because the structure of a confidence interval for the T with the standard population unknown, it's basically the same setup as the Z. It's just instead of Z alpha over 2, you have a T alpha over 2, and instead of sigma, you have S for sample standard deviation. So it's essentially the same setup. Now this, to do the T confidence interval, yes, that's going to be in the calculator, but you still have to know how to read that chart, because for sure I'm going to ask one question at least where all you're doing is what we did with these last two problems. You're just getting the value off the chart. So you'd still would have to know how to read the chart. So make sure, so don't get sloppy and think, okay, I don't have to ever look at that chart. To actually calculate a confidence interval, that's true, you don't. But to actually get the chart value, you're going to need to look at the chart. So, all right, so that's basically it. So now we're going to just take a look at some examples. So once you kind of get the hang of this, the only difference is now, making sure you know when it's a T and when it's a Z. So if you're doing a problem on a test or whatever, and you're doing it and you're not getting the right answers, go back and look at the problem and make sure that did you choose Z when it was supposed to be T and vice versa. That's usually a very common mistake. Now, of course, if both answers are there, that's a different problem, but because you'll think you got it right. But if you didn't find the right answer, just check to make sure that you're using the correct T or Z. Because other than that, these aren't very difficult. So let's take a look at this example. Random sample of 7 computers. Sometimes people give me a hard time in class when they say they don't like words as numbers. It confuses them. So 7 computers. The mean repair cost was 100 and the standard deviation was 4250. So, you obviously assume that's a sample standard deviation, because to be population, it's got to either have the word population in front of it, or it will have that sigma symbol there. One of the two. Assume the variable is normally distributed. Now, don't let that make you think this becomes a Z distribution. That's not it. That's just one of the conditions for this to even be able to be done as a T distribution. And all we have are Z's and T's. We're not, if it's got one of them's got to apply. So, that's just part of the. Now, it should say that every time. You might run into something. I think most of the homework problems should be, hopefully all of them, will clearly say, assume it's normally distributed. It kind of just sort of needs there. In fact, one thing I'll give you a hint if you're doing the MyMathLab homework is the one of the, what sometimes like the last part of a multi-part problem, let's say, or even maybe the first part, what condition must be met. So you're kind of looking for that part. So I'm saying, the variable is normally distributed. That will be the right answer every time for that when that comes up. What condition must be true to do this t-distribution. Okay, this one's asking for the margin of error and then constructing the 95% confidence interval. Something, just in case we ask, because I could ask margin of error as its own question, even. Remember, the margin of error is always the part that's after the plus and minus. So we're using him explaining why we're using the t, less than, and the less than 30 also is a clue. As I mentioned earlier, in our world, I'm going to treat less than 30 as being a t-distribution. I'll make sure those don't have the population standard deviation. So n is 7, x bar is 100, s is 4250. And then now let's get that we have 7, sample size is 7, it's 95%. So I guess I can just bring the t-chart up here instead of scrolling back up the notes. Too many pages now. Oh, and I already forgot what the percentage was, sorry. I know it's 6 degrees of freedom, 95%. So it's 6 degrees of freedom, 95%. Right there. 2.4469. So you're 6 degrees of freedom, so be careful that you go, across that row straight across. 24469, very good. And then the margin of error will just be the part, like I said, after this. So it's just the t times standard deviation divided by square root of n. So it's 2.4469 times 4250 divided by square root of 7. And then you get 39.31. So the sample mean plus and minus that margin of error is what creates your confidence interval. So we have 100 minus 39.31 gives you 60.69. And then 100 plus 39.31 gives you 139.31. I'll even put the keystroke thing in there. But I'm going to do this one actually, even though it's written here. I'm going to go ahead and do it. This will be our first t-interval problem. So it won't be difficult. Just be careful that you're still. There's from a previous video I did. That z-interval is still sitting there. Don't want that, but I want to be in the same area. Stat, test. I want number 8 down there that says t-interval. T. There we go. Stats. The mean was... Great, I know the standard deviation is 4250. I'll do what I can remember here. Then I'll go back. Oh, it's 100. All right, I can go back and get 100 in there. Means 100. Just got the standard deviation. Sample size was 7. Confidence level is not 0.95. Calculate. There it is. 60.69 to 139.31. Fantastic, as my math lab would say. Okay. Average grocery bill at the cash register, sample of 17 shoppers. The store's 5380 with a standard deviation of 1840. Assume the grocery bills are normally distributed. That's our permission to use the t-distribution. Determine the 80% confidence interval for the population mean. All right. So I wrote down some of the pertinent information here. 5380. N is 17. S is 1840. And then I'll look up the t. So n is 17. That means 17 minus 1, 16 degrees of freedom. Very important. So 80%, 16 degrees of freedom. So 80% is the second column. We're about to lose the 80 here now, so let's bring this in here. 16 degrees of freedom. I do believe we have something there, 1.3368. Excellent. So there we go. Now you can just plug it right in the formula. So this is kind of like if you're just using a regular calculator. But as I mentioned before, even if you're using the TI, know how to look up that critical value on the chart, because that's going to be its own question also on a test. So, but this part here, if you're using the T-interval process, you don't need to do this. But so it's 53.80 plus or minus the 1.3368 times the standard deviation of 1840 divided by square root of 17. And then there, you see I have it displayed right here as if it was just being done with any kind of scientific calculator. It doesn't have to be a TI to do this part. And I got 47.83, and I got 59.77 as the upper number. I'll run through the T-interval real quick. Test T-interval. 5380 sounds familiar, but I better go back and look at this one. Oh. 5380, 17, and 1840. I want to double check this. I don't feel good about this. Before I hit calculate, let me. 5380, 1840, and 17, and then it was an 80%. Standard deviation was 1840. So here's our output. That looks good. 4784 to 59.77. Terrific. Let's see what we have here. We're testing. That talks about the normal population right up here instead of in the problem, which is fine. Laboratory tested 12 chicken eggs and found the mean amount of cholesterol was 193 milligrams with a standard deviation of 15.4 milligrams. Construct a 95% confidence interval for the true mean cholesterol content of all such eggs. So notice, if you watched my other video on the Z distribution, when I mentioned that confidence intervals can be expressed as an interval in parentheses or like interval notation like this, where you just have the population mean mu in the middle. All right, let's see what we have. N is 12, X bar is 193, S is 15.4. If N is 12, degrees of freedom is 11, so we need 95%. 11 degrees of freedom. Right there, 2.2010. I'm sure we can leave off that last zero. 2.2010. So here's the setup using the formula. 193 plus 2.201 times 15.4 divided by the square root of 12. So you see I get 138322 to 20278 right there, which is this answer right here, same thing. I'll skip the input process here because we'll do it on another problem. But so I did the T, notice it just says T interval there, very important. So, and we got the correct answer. So I'll go ahead and move on to this one. All right, so it's supposed to fill, this bus station is supposed to have 6 ounces of soup. 10 cups of soup are brought with a mean of 5.93 ounces and a standard deviation of 0.13. Construct a 99% confidence interval for the true machine fill amount. Assume the population is normally distributed. Okay, everything's good here. N is 10. The 5.93 is a sample mean. Just be careful with the 6 in the first sentence. You're not really using that. It's just sort of giving you information in the story that you're supposed to have 6 ounces of soup. It's just not a number we put in the calculation. And 0.13. So it's a 99% interval. So if N is 10, degrees of freedom would be 10 minus 1, which is 9. 99 and 9 would be right here. 3.2498. So just kind of using a regular calculator, you'd go 5.93 plus and minus 3.250 times 0.13 divided by square root of 10. And you get 5.796, 6.064. So it looks like answer E here is correct. I'm not showing the output here, or the input, but there's the output, so no problem. It's correct. So I would have entered everything in there. Like I said, I'll be doing another one here in a minute. But this one, I wanted to show, this was an example of something I mentioned earlier that may or may not happen. I mentioned, if you found the wrong answer, then, or you couldn't find the right answer, I should say, that, it may be using the Z or T. But this is one where, unfortunately, that I just showed that if you did the Z interval process, it actually, I'll zoom on this a little bit, it yields answer D. If you did the Z instead of the T, it's that answer D. So that one, you wouldn't even know that you did it incorrectly. So it could be a combination of both. That could happen, or you just flat out don't find the correct answer because you chose the wrong process. So just be very, very careful, and these will be easy. Sample of 27 Exxon customers use an average of 16.1 gallons to fill their vehicle with a standard deviation of 5.4 gallons. Assume the number of gallons is normally distributed. Determine the 99% confidence interval for the mean. Let's get the chart value. So if N is 27, we have 26 degrees of freedom. So it's that far right column. Let's scroll way down there. And we got this, 2.7787. And then there it is. So there's your critical value. So we go 16.1 plus and minus 2.7787 times 5.4 divided by the square root of 27, which gives us the interval of 13.21 to 18.99. I'll put this one in the calculator. Test T interval, not T test. Actually, on the unit hypothesis testing, we'll be using those first two, Z test and T test. That's sometimes where it gets confusing once you learn that, and then you got to pay attention. But it's real straightforward. Interval means confidence interval. That's all you have to really remember. So if you want to do a confidence interval, you're choosing either number 7 or number 8. Simple as that. All right. Let's see. I don't know what any of these numbers were. I don't remember them. 16.1, 5.4. I think N is 27, but I already forgot the confidence level anyway. 99%. N is 27. Oh, one thing I want to mention, I didn't mention this earlier, but so if you were thinking this, because sometimes people ask me this in class, but that's all right that I said it now. Notice that, when I'm using this formula, and we've been doing it correctly every time, so don't worry about it. You're dividing by the square root of whatever n was. That whole n minus 1 degrees of freedom is only used for looking up the critical value on the chart. The formula uses n itself. So I just want to throw that in there, just in case you were wondering. And same thing with the calculator. You put in whatever n is. You don't put the degrees of freedom in here. You just put in n and go from there. So, okay. So that subtracting 1 is only for chart purposes. The critical value from the chart. So I want to clarify that. And calculate. Let's see what we got. I think that was it, right? 13.21 to 18.99. Alrighty, we'll call that one a nice work there. Alright, since I'm not using a tablet PC here, like I do when I lecture in class, and I won't write this out. I'm just going to go ahead and, obviously you can email me if you have a question or something. I'm just going to show the calculator input is all I'm going to do for this one, because if I try to write with a mouse, I'll look up the critical value though. I'll do that. But if I try to type everything in there using a mouse pad, it's going to look like the stylus was between well, this doesn't have a stylus. This one doesn't, but it would look like I took a tablet and put the stylus between my toes or something. But anyway. So 13 hotels, average room rate 172.10 with a standard deviation of 2390. So less than 30. Sample standard deviation. Together that makes that a T. Normally distributed. That's also the condition for the T. And we want a 99%. And I seem to be hooked on 99% here, don't we? But anyway, so 99%. 13 is in, so it's 12 degrees of freedom. So if you are using the formula to do this instead of the calculator, I want to make sure I show you what the critical value is. So it'll be 99 far right, 12 degrees of freedom. You'll use 3.0545 as your critical T value in that formula. So if you are doing that way, then every other number is given in the problem. If you're doing it that way, this would be a good one to practice. Well, obviously the homework will do it. The online homework will do it too. But alrighty, so let's put it in the calculator real quick and see what we got. That was 172.10. And it's 13. Now I got to go back and get that standard deviation because I don't remember. 2390. And it still has the same confidence level of 99 that we used before. So I don't have to change that one. It's already 99. Calculate. So it should be 151.85 to 192.35. And there it is right there. Answer C. That is correct. All right, beautiful. Alrighty. Random sample of 27 UHD students and obtained their GPA. Business students, sample mean GPA was 3.15 with a standard deviation of 0.8. Assume the GPAs are normally distributed. Construct a 90% confidence interval for the mean GPA for all UHD business students. So once again, we're still trying to do the same thing with a confidence interval. We're trying to come up with an interval that we would think the average for all UHD business students, because that's the population of this problem, is UHD business students. So, okay, this should be pretty straightforward. I wrote down that. So n is 27. We have 26 degrees of freedom. So let's go look up 90% and 26 degrees of freedom. 90% is in column 3. So now I have to scroll down. You won't see that anymore, but 26 right here, third column, 1.7056. And then if you're doing the formula, that should be pretty straightforward there, I believe. 3.15 and then 1.7056. Oh, I didn't mean to erase that. Undo. Times 0.8 divided by square root of 27. So you have 2.89 to 3.41. I'm not going to retype all this in, but it shows all the entry right there for the t interval. Everything's right there. And then there it was. Pretty much yielded the same answer. Now, I generally don't do this on exams, but there might be something in the online homework, or maybe some point in the future I might do this on an exam, but right now I don't at the time of this video. But this is a lot more. It's a lot easier if you put this in the calculator. But so because of these t distributions are often smaller size samples, I've seen sometimes problems where they just give you the individual data values without the mean and standard deviation. So here you have 5 numbers. So it's not doing anything that we haven't done before. It's just more tedious this way. But with 5 numbers, it's not too bad. If we were doing a z distribution with about 60 numbers, that would just be downright rude, unless we were using, Excel or something to do it. Or the calculator, of course. But what all that means is, so what we're saying is we have these 5 numbers. That means we have to come up with the sample mean and sample standard deviation that would normally just be given. So you see, like the last problem, it gives you an x bar, it gives you an s. We just have to calculate that. We know n is 5 because there's 5 numbers here. So, all right, I kind of went through a long and drawn out process here. Don't worry about this. Unless you absolutely have to do it this way because you have no other way to come up with the standard deviation. Obviously, the mean's simple enough. But I'm actually going back and using one of the old formulas to do that, but you don't have to if you can get it without doing that. Now, let's see what we have here. So long story short, I calculated, well, the mean was 5. That was easy. I got 2.9155 for the standard deviation. Now I need the critical value, so it's a 90% confidence interval. We know n is 5 because there are 5 numbers, so it's 4 degrees of freedom. Let's go get that number off the chart. %, 2.1318. I'm not going to worry about changing this right now, but I used to use a chart that had it 3 decimal places. So let me double check that number. So it was 2.1318, which would round to 2.132. I mean, you use 4 decimal places, since I have 4 decimal places, but yes, this was based on I used to use a chart that only had 3. So that's why it's still the correct number though. So you plug in the number in the formula. If you're doing it this way, you get 2.22 to 7.78. But let me show you how to do this in the calculator. I also showed how you can get the mean and standard deviation using Excel if you needed to. But if you have the TI, don't even worry about that Excel. All that Excel on the next page is doing is it's simplifying this process right up here. But if you're not doing that process, then don't worry about it. All you've got to do is put the numbers into a list. So I go Stat, Edit, List. I'm going to go up here because I don't want all that. I'm going to clear. Now that's empty. So it's 2, 3, 4, 7, 9. And I'm going to go second quit. Now, I could do 1 var stats, to get the mean and standard deviation, but we don't have to even do that because we can go straight to the t distribution and do something we haven't done before. So I'm going to go stat, test, t-interval again. Now, here's the difference. This time you choose data instead of stats. Stats always means you're entering the mean and standard deviation. Data means, hey, we'll take it from a list and we'll calculate it for you. We're saying we're that nice. So we have our numbers in L1s. That's a good reason. I don't know what that just needs to be 1. I don't know. Just don't ever change it. But yeah, so put your data in L1s. You don't have to change the list. So it's going to take that and do everything. The mean, standard deviation, the entire interval. I've already forgotten the percentage. I want to say it's 90, but let me double check. Yes. All right. So if this is in one of the homework problems, this will certainly be convenient. And like I said, if I ever decide to do it in future exams, future semesters, I mean. Calculate. And there it is, 2.22 to 7.78. It's telling you the mean and standard deviation right there, just for grins. Yeah, and there's the same input there. I just wanted to show you that, 'cause that's a little bit, we haven't done it that way before. And this is just putting it in Excel using data analysis to get the mean. So there's the X bar is 5. There's the standard deviation, 2.91, blah, blah, blah. But actually this gives you, and then there's that N is your count. This confidence level right here at 90%, if you choose that 90% as a selection, that's the margin of error right there. So if you were, that would be probably better than using, the calculator is the best way to do it, but instead of calculating the standard deviation using the formula, so you would just do, if you did this and chose 90%, in other words, to get the confidence interval, all you have to do is go like that, 5 minus this number. I just rounded 2 decimals. And then 5 plus that number. So it's 5 plus and minus, that's the margin of error. Would be nice if it told you that was a margin of error, wouldn't it? But oh well, so much for that. And I think that's the last one, because the last page is that whole blurb about the degrees of freedom and all that stuff that you don't have to worry about. So make sure that's it. So yes, that's it. So that concludes this video on confidence interval for the mean, population standard deviation unknown, t-intervals.